All right, we have one other pattern type of reaction to talk about. That's called an oxidation-reduction reaction. This involves transferring electrons from one atom to another. Either oxidation reduction, the other term we use is redox. And many of them will involve the reaction of a substance with oxygen, but not all of them do. So redox reactions, one category would be combustion, where something reacts with oxygen to form, in this case, water. If it's a carbon-containing compound that's combusting, it's going to make carbon dioxide in water. And electrons are being shifted. We can also get redox without combustion. So if you take solid sodium and solid chlorine, or not solid chlorine, gaseous chlorine, elemental chlorine, and the electrons are transferred from the sodium to the chlorine, then we get solid sodium chloride. Our sodium is oxidized, loses electrons. The chloride is reduced and gains the electrons. Can also think of the reaction of metals with nonmetals as oxidation reduction. And they also involve converting free elements into ions. So here you have sodium reacting with oxygen to form sodium oxide. The electrons are transferred from the sodium to the oxygen, similar with the sodium chloride. So converting free elements into their ions. Okay, oxidation and reduction. I've mentioned this all involves moving electrons around, and our electrons need to go somewhere. So if one atom loses electrons, another must accept them. These redox reactions are ones where electrons are transferred. Atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. There are a couple ways to remember this. My personal favorite is that Leo the lion says grr. So lose electrons, oxidation. I tend to look at a reaction and go, oh, this lost an electron. Oh, that's oxidation. That's why I like this acronym. And then he says grr, gain electrons, reduction. That's an R. The other one you might know is oil rig. Oxidation is loss, reduction is gain. Either one of those is fine, or you can just remember what they are. You know, if you don't want to use an acronym, that's fine too. I don't really care. Okay, we need to keep track of the electrons. So for reactions that are not as simple as the ones we just looked at, they're not a metal plus a non-metal or don't involve oxygen, we need to be able to keep track of the electrons. The way we do that is through something called oxidation state. Now, oxidation states are going to look like ion charges, but they are not the same as ion charges. They are imaginary charges based on a set of rules we're going to go over. Ion charges, on the other hand, are measurable and they're real. So our rules for assigning oxidation states, and remember these rules are in order of priority. So rule number 1, free elements have an oxidation state of 0. Monoatomic ions have an oxidation state equal to their charge. So the sodium ion has an oxidation state equal to its charge of positive 1. Chloride is minus 1. 3A, the sum of the oxidation states of all the atoms in a compound is 0. 3B, the sum of the oxidation states of all the atoms in a polyatomic ion equals the charge on the ion. So for a compound, you need to be 0. If it's a polyatomic ion, it needs to equal the charge. Number 4, group 1 metals have an oxidation state of +1. Group 2 metals have an oxidation state of +2. And then rule number 5 here is the one you really need to keep in mind. In their compounds, non-metals have oxidation states according to the table below. And again, the table is in order of priority. So the highest priority is fluorine, has an oxidation state of -1. Hydrogen, oxidation state of +1. Oxygen, oxidation state of -2. Group 7A, which are the halogens, the rest of the halogens under fluorine, have an oxidation state of -1. Group 6A, so that's the group under oxygen, group charge of -2. And then group 5A is -3. Notice carbon doesn't fit in any of those categories. So carbon, you always have to assign everything else in the compound and then do the math to figure out what is left over for the carbon. Because remember, there was a rule farther up about it needs to add up to 0. So for example, determine the oxidation state of all the atoms in a propanoate ion, C3H5O2-. So we can skip the free elements, free ions. So the first thing that applies is rule 3b. All the charges need to add up to -1. Then everything is nonmetals. So our next rule that applies is rule 5. And in that table, the first one that applies is hydrogen is +1. So we have 5 +1s. Then our oxygen is -2. So we have 2 -2s because each individual atom gets its own oxidation state. And so then we are left with the fact that they need to add up to -1. So each carbon is assigned a charge of -2/3 because there are 3 carbons for a total charge of -2. So each one gets a -2/3 oxidation state. Sorry, not charge. And they can be fractions in oxidation states, unlike charges. So here's a practice slide for you. Assign an oxidation state to each element in the following. And I would pause it, work through the rules on your own, and then I will talk through the answers. So bromine, rule number 1, 0. Potassium ion is a +1. Lithium has a +1. Fluorine is a -1. Carbon dioxide, the oxygen is assigned a -2. So our carbon, since there's only one of them, ends up at a +4 because it has to add up to 0. Here our oxygen is again assigned a -2. Our sulfur, we know that we have to, whatever our charge on sulfur plus our 4 times our -2 has to add up to -2, which means our sulfur is going to be a +6 charge, or oxidation state. And then this one down here is kind of an exception one. So our sodium, farther up in the list, is assigned a +1, which means our oxygen, because it has to add up to 0, is assigned a -1 in this case. So there's the answers and the rules that it came from. Okay, here's another practice. Determine the oxidation number of the red element in each of the following compounds. I'll give you a minute to, well, I suppose you can pause the video. The phosphate here, our H's are, we have +2 in total. Our oxygens are -2, so -8 overall. We need to add up to -1, and so our phosphate there is going to be a +3. 5. Our oxygens here are -2. There are 6 of them, so -6. So our sulfur is a +4. Here our oxygen, -2, so we have -8 overall. So our nitrogen has to be a +4. And so where do we have +5, +4, +4? Letter C is our answer. Okay, now we can look at overall reactions with oxidation and reduction. Another way to think about it is oxidation will occur when an atom's oxidation state increases during a reaction, and reduction occurs when an atom's oxidation state decreases during a reaction. So we can use oxidation states to kind of keep track of electrons. So if we increase oxidation state, we have lost electrons, lost the negatives. And reduction, we gained those negatives. So here, if you assign oxidation states, we see that our carbon goes from a -4 to a +4. So it has been oxidized. Our oxygen goes from a 0 to a -2. So it has been reduced. Right, so oxidation and reduction need to occur simultaneously. In other words, you can't have free electrons just floating around. If one atom loses the electrons, another atom needs to take them. Now, more terminology for you. The reactant that reduces an element in another reactant is called the reducing agent. So agent means it's making something else reduced. In other words, it's the element that is oxidized. And similarly, the reactant that oxidizes an element in another reactant is called the oxidizing agent. And the oxidizing agent will contain the element that is reduced. So if you remember that whatever's oxidized is the reducing agent, and whatever is reduced is the oxidizing agent, that will help you. So agent means what it's doing to something else. All right, here is a big oxidation reduction problem for you to work through. Assign oxidation states, determine the element oxidized and reduced, and determine the oxidizing agent and reducing agent in the following reaction. So step 1, assign oxidation states. Our iron is going to have an oxidation state of 0. It's a free element. Our MnO4 minus, our oxygen is going to get assigned a 2 minus. There are 4 of them, so that's a total of -8. Needs to add up to -1, so our manganese is a +7 there. Our H pluses are all +1. Our iron goes to +3 because that's its charge. Our oxygen is still a -2. Now it's a total of -4, needs to add up to 0, so our manganese is now a +4, and in our water, our oxygen is a -2, our hydrogen is a +1. So you can see the elements that have changed oxidation states are our iron and our manganese. Our iron lost electrons, went to a +3 state, so it is oxidized. Our manganese went from a +7 to a +4, so it gained the electrons, so it is reduced. And whatever is oxidized is the, I'm going to change colors, reducing agent, and whatever is reduced is the oxidizing agent. So you see how once you assign the states, you can figure out what is oxidized and reduced, and then whatever's oxidized is the reducing agent, whatever is reduced is the oxidizing agent. And there's that worked out for you. A couple more problems. Assign oxidation states, determine the element oxidized and reduced, and determine the oxidizing agent and reducing agent in the following reactions. So here tin is a +4, calcium is a 0, This tin is a +2. Calcium is a +2. So our calcium here was oxidized. Our tin was reduced, which means our calcium is the reducing agent, and our tin is the oxidizing agent. Then in our other one, our fluorine here is a 0, sulfur is a 0. Fluorine here is a -1, sulfur has to be a +4. Fluorine gained an electron going from 0 to -1, so it was reduced, and our sulfur was oxidized, which means our sulfur is the reducing agent, and our fluorine is the oxidizing agent.